All right.
Nice. All right, thank you. Okay.
Okay.
Yeah, so let's begin. Yeah, someone asked what topic we will do today. I'm planning to teach something a little bit more basic. So I suppose last time uh Jia Heng already taught you guys length chasing and angle chasing. So today let's kind of talk about circles, and we're just gonna introduce uh the power of a point and then learn some techniques that we can use for that. So let's recap. Let's recap because I think Jia Heng also mentioned a little bit of that notion. So okay. So if we're given a circle, let's say a circle like this, say the center is O and the radius is R, right? Then we will define a function. So let's say this, I can call this circle omega, let's say. I can define a function that takes in any point and gives you a number. Actually, let me use a different symbol. This looks like W. Let's say this circle is omega. Then I'll define a function called the power that takes in any point on the plane and gives you a number. And it will be defined like this. Our point is equal to OP squared minus R squared. So with this simple definition, we haven't learned any properties yet. I thought omega is I'm using the uppercase omega here. Yeah, the one you're using is the lowercase. But I didn't want to use it because it looks like a W. So so now we can kind of see a lot of properties. For example, the power. I'm just gonna not write the subscript when I'm lazy. It's 0 if and only if P is on the boundary itself, right? P is on the circle. And well, and if it's inside the circle, it's negative. If it's outside the circle, it's positive, right? Hmm. So this power of a point thing has something to do with the intersecting chord theorem and the intersecting secant tangent theorem. So when we have a circle and we have any point inside, or let's say outside the circle, then if we choose any chord, this let's say it intersects the circle at A and B, then we can prove that PA times PB is equal to the power of P with respect to this circle. And here I'm using what we call signed lengths, which means on a given direction, you can choose one direction as positive, the other direction as negative. It doesn't really matter because whichever convention you use, this formula is still true because PA times PB in this case will be negative since they are in opposite directions. And this is still true if P is outside. If P is outside, like I can just literally draw on the same. Never mind. P is outside like this. This A, this B. It will still be the same thing. In this case, PA times PB will be positive because they're in the same direction. And that coincides with our property that the power is positive outside. So PA is not the same as AP. Yeah, so if well, for sine lengths, then they are opposite of each other. But well, it depends on what you're working with. It depends on whether you're using sine lengths or regular lengths. AP times BP equals PA times PB. Yes. So even if you're working with sine lengths, that's also correct because if you flip the two directions, you're just negating the value. Right? So this, of course, this requires proof, and proof is literally by similar triangles. You can draw the diameter that's passing through P. And what happens is these two triangles are similar. Why? Because this is equal to this is equal to this, right? This angle is equal to this. So when these two things are similar, you can use ratios and to prove that px times pa, px times py equals pa times pb. And px times py is way easier to calculate because it is just the radius plus op times, or I should say, op plus the radius times op minus the radius. And this is op squared minus r squared, which is the power. This is by definition here. Okay, cool. And it works the other way around as well. The converse is also true if you have 4 points that satisfies this relation. That means they form a circle. That one's quite easy to prove. The converse, you uh just do it the other way around. Right? Use this and prove that the triangles are similar, so the angles are the same, so they're cyclic. Okay. Now consider, well, two circles. Now we have two circles. Two distinct circles. Say something like this. Let's say omega 1 and omega 2. Then, given any point, we can define the power of that point with respect to omega 1 and define the power of that point with respect to omega 2. Right? Now, the question is, what's the locus of the points where these two are equal? So, where these two are equal. And the answer is, anyone remembers? So you fix two circles, and now you want to find the set of points P such that these two are equal. It's a line, yes, and the line itself is called the radical axis. And Jia Heng, I think, proved it to us to y'all last time. So a simple proof that you can use is by doing a coordinate bash by, let's say, you can just choose the coordinate system so that it's centered at one of the circles, and the other circle is on the x-axis as well. And then it's quite simple to prove that. I mean, simple as in you just expand this into the coordinates, and what you find is a linear equation, right? So it's a line. So, and if it's a line, it's going to be symmetric, right? It's going to be because this diagram is up down symmetric, so that line must be vertical like this. It can't be horizontal. Okay, so this is called the radical axis between omega 1 and omega 2. So for disjoint uh yeah for disjoint circles, it's quite hard to see where the radical axis is. But there are ways that you can kind of construct it. One of the ways being drawing two tangents. And this is probably not accurate. Hang on. You draw two tangents like this. These are the external tangents. Then, yeah, the midpoint of the two tangents must lie on the radical axis because the the power of the point is exactly equal to the tangent. In fact, we kind of didn't say this just now, but basically, if you choose A and B to be right here, then the power is just PA times PB, which is the tangent squared. So midpoint, midpoint, that would be the radical axis. If the two circles have a common chord, then these 2 points are obviously on the radical axis because this is where the power is equal to 0, right? Power is 0. Power is both 0. But then a line, we already have 2 points on the line. You can directly know what whole line is, which is just the whole chord. Right? Everyone follows? Any questions so far? Because when you have the very the degenerate case where the two circles are concentric, then the radical axis won't be defined. Ah, someone has a question. Take your time to type. Meanwhile, I'll draw the diagrams for the next part. Or I'll just continue first, and then when you send a question, I can come back to it. Okay. So now if we have three circles, right? Let's say omega 1, omega 2, omega 3, right? Then let's say I look at the radical axis of omega 1 and omega 2. So that would be something like this. And we look at the radical axis between omega 1 and omega 3, we get probably something like this. Oops. And then we look at the radical axis between omega 2 and omega 3. And the claim is that they will meet at a common point. And why is that? Why the three? Why do the three radical axes meet? Let's think about it from the definition. Ah, yes. So because by definition, the radical axis is the points where the two powers are equal, right? So if you have two radical axes, let's say this one. So this one is where the power with respect to omega 1 is equal to the power with respect to omega 2. This one is where the power of omega 2, power with respect to omega 2, is equal to power with respect to omega 3. Then, of course, in the intersection of these is the point where these two equations hold. But when these two equations hold, the power with respect to omega 1 will be equal to the power with respect to omega 3, right? If A equals B, B equals C, then A equals C, right? Transitivity. Yeah, and it's just a simple reason why they meet like this. Yeah. If anyone has any questions, just type it in the chat. I will come back to the questions. Or if I'm going too fast, if I'm going too fast, you can also tell me. Okay. Now, right. Which means, well, this is the case where the three circles are disjoint. But if the three circles are pairwise intersecting, then we have a very beautiful relation, which is the three common chords must intersect at a single point. Right? Because the common chords are the radical axes. Yes, exactly. So the point the common point here is where the powers are equal. The powers are not zero, but the powers are equal. So this point, this concurrency point is called the radical center of the three circles, right? And there's a very good strategy, which is the converse of this statement. A very good strategy to prove that 4 points are concyclic. It's a very good technique that we should know. If we have 2 points, let's say something like this. We have P, and then we have two chords like this. And then let's say we draw another circle. That the chords meet like this, right? We draw a third line, this, and then we put in these 4 points. If AB lies on omega 1, CD lies on omega 2, then ABC is cyclic. Yeah, exactly. So it's the converse. So basically what I'm drawing here, if you have two circles like this, and you draw these chords, then these 4 points will be cyclic. And to prove this, is x and y, x, y, a, b, c, d. So PA times PB equals PX times PY because of the first circle, because of omega 1. And PC times PD is equal to PX times PY, the common chord is due to omega 2. So these two would imply PA times PB equals PC times PD, and hence ABCD is cyclic. This is a very, very, very nice way to prove that 4 points are cyclic. And it's used in quite a lot of cases when we do problem solving. Yeah. So, okay, now let's see. Let's look at an exercise, for example, of how we can use this. Say we have a triangle ABC. Oh, sorry. Scroll up a little bit. Yeah, sure. Okay, cool. So let's say there's a triangle ABC, there's an acute angle triangle ABC. And then let's say the circle with diameter AB is circle with diameter AB intersects altitude CC prime. Let's say M and N. And let's say the circle with diameter AC. So by drawing the diagram, we're kind of giving a little bit of spoiler already, because such a diameter of AC, it must go through C prime, because that's where it's 90 degrees. Let's say intersects the altitude BB prime at 2 points, P and Q. Then you prove that M and PQ is cyclic. How do we use this fact? I mean, how do we prove this fact? Think about it. Ah, so there is a center of a triangle called the orthocenter, which I'm not sure if we talked about this before because I'm not sure if Jahan. Yeah. So yeah, so let's talk about the orthocenter. So a triangle, and this is one of the few nice centers that you can have. If you have a triangle, the three altitudes they must meet at a point, and this point is the orthocenter of ABC. It might be in the triangle, it might be outside the triangle. So if ABC is obtuse, then the orthocenter here is a bit ugly because the altitude is like this. Prime is here. You'll meet outside, so H. Okay, so uh, and we can prove this in quite a few ways, but let's just take it for granted now. You can use quite a few techniques to prove it, but maybe I'll talk about it afterwards when we talk about other centers. So here, well, why is it called the orthocenter? First of all, because the prefix here or prefix here, orthocenter or TRE, it stands for orthogonal, and orthogonal means forming right angles, right? What is MNBB prime? Oh, BB prime is the altitude, and MN is where the altitude CC prime intersects the circle with diameter AB. This is the circle with diameter AB. This is the circle with diameter AC. It stands for orthogonal, and orthogonal means forming right angles. Okay. AC the diameter. Yeah, AC the diameter for this circle. So, so yeah, so someone said orthocenter. Now, the orthocenter is naturally the intersection between BB prime and CC prime, right? So let's call it H. So what does that mean? What can we use about H? Because we just took two lines, took the intersection and call it H. So we never really use any property of that point yet. So we're just calling the intersection a label. So we have to kind of exploit some properties of it. So for example, it lies on the third altitude. That's a non-trivial fact. So let's draw a H, and AH, of course, it must hit this intersection, which I already implicitly assumed in the diagram that they meet at the line BC, which is also not very direct. But if you think about it, the two circles, one with diameter AB, one with diameter AC, wherever they hit on the line BC, it's gonna form right angles because diameter. So they kind of lie on the same point. So this is actually AA prime. Yeah. So AA prime is the radical axis between these two circles that we have over here. And we see, if you can see sort of a familiar configuration here, familiar with the diagram that we've seen just now. So so H is sort of like the radical center, but it's not the radical center yet because that's what we want to try to prove, right? We want to prove that MNPQ is cyclic. And before knowing that, we cannot say that H is the radical center yet. But we can prove it the other way around and say, okay, use the same technique. HP times HQ equals HA prime times HA. Well, I mean we haven't proved that MNPQ is cyclic yet. So we cannot say H is the radical center and hence MNPQ is cyclic. Logic doesn't work the other way around. So HP times HQ, so HN times HM equals HA prime times HA. Yeah, so then the HP times HQ equals HN times HN, and MNPQ is cyclic. So that's one way you can do it. So when there's a lot of circles, you can consider something like this. The power using the powers. So even though the notion of powers, you don't really have to use the notion of powers, but you can use the techniques that you can learn from learning the concept. Right? Okay. Cool. Mm, yeah. So now let's because we were speaking of auto centers, let's have a brief summary of centers of a triangle, the famous ones, and their properties. Let's start with the basic ones. So we have the centroid, where we take the medians. Whenever we take the medians, they concur, and so well, that point we call the centroid G. There are many ways you can construct it, not just by medians. You can also, if you're working in a vector in a in vectors, then the vector G is the average of the vector A, vector B, and vector C. This would come into play when at some point you guys learn let's say barycentric coordinates, then this will be quite useful. Sorry, divided by 3, not divided by 2. Okay. And also these form in a 1/2 ratio. 1/2 AG over G A prime is a 1/2 ratio. Hmm. So then we can talk about, let's say, the circumcenter, which is the center of the circle that circumscribes it. So you can say it's O. So that means by definition, these three are equal, which you can then use to prove a lot of angle properties. So like let's say this is 2 times the angle of A. It's from the basic circle properties. We'll use 2A and so on and so forth. So you can get a lot of things from there. Okay. Then there's also the auto center. So I'll present one way to prove that they are concurrent. You can use vectors to prove again by bashing it out, but that will be quite ugly. So another way to do it is recall that the circumcenter is the point where you take perpendicular bisectors of three sides, right? So it's O, which makes sense because you want to find a point that's equidistant to all three vertices, right? Right. Here, in this case, we're gonna do something that's quite nice. We are going to copy the triangle. Let's say I copy it like this. I rotate it around the midpoint of AC. So then that's a parallelogram. Mm, well, I'm not going to talk about isogonal conjugates yet, but I probably will afterwards. So ABC, then we have, let's say I rotate it, so this is, let's say, B prime, and I go the other way around, form a parallelogram on the other side. It's going to be C prime. Then I'm going to do the same right here, it's A prime. Then, well, we have four congruent triangles over here. And this is obviously a straight line because because this is equal to this and this is equal to this. So they all add up to 180. So now, whenever we take an altitude, this A prime is actually the perpendicular bisector of B prime C prime, because first of all, it forms a right angle. If it forms a right angle with B prime C prime, and second of all, these two are equal since they're congruent. They're all equal to BC. So the altitude of A is the perpendicular bisector of B prime C prime. Oh, sorry, I used too many A primes here. Let's call it A prime prime. So now, since we can show that the circumcenter exists, we can look at the circumcenter of A prime, B prime, C prime, and that will be formed using the perpendicular bisectors. But the perpendicular bisectors are the altitudes, are the altitudes, so we can say that they are concurrent and call it H. Is that okay? And then the next center is the incenter, which is the center of the circle that's inscribed in the triangle. Yes. So A, B, C. Right. So what are the properties here? So we have to look at, let's say, because it's tangent to the three sides, we have to use that fact. If it's tangent, that means the actual tangent lines, they will be forming right angles with the center at that point. So this is like this, and these are all equal because it's a radius. So by symmetry, these two are the same angles, right? They're just reflections. Like if you cover up AC, it's literally just two lines and a circle. Right? If you cover up AC, it's just literally two lines with a circle. So the center obviously lies on the angle bisector. So yeah, then you can do the same for the other three sides. So indirectly, you already prove that the angle bisectors concur. Okay, yeah. Now, there's another point that's really close to the incenter normally. So don't get mistaken by it. If we have the incircle again, me just draw a perfect one. This, this, this. The in center will be different from the point formed by connecting the tangential points to the opposite vertices. So if it's A prime, it's B prime, it's C prime. This is not the in center, and I've seen people make this mistake quite a lot of times. This is not the in center. It's slightly offset, and you can kind of hopefully see why, because AA prime is different from AI. So if you look at this from an angle, this point and this point, they are perpendicular to BC. If you connect AI and you connect AA prime, there are two different lines. This new point, which is again non-trivial that they actually meet at a point, but we can prove that they meet at a point by using Siva or Menelaus, which I'll talk about later. This point is less commonly known, but it's good to know. This is the Gorgon point. Just telling you this because many people think it's the in center because it kind of looks very, very close to being an in center. There's an in circle. There are three lines, so some people might mistake it. Right. Now, if you have an in center, we also have X centers. So an X center is where we do it. We inscribe a circle again, except we don't inscribe it within the triangle. We still make it tangent to all three sides, but we put it outside the triangle. So for example, A, B, C. And let's say we have a circle like this. This very hard to draw, Let's draw a circle. Oops. Do this. There we go. Sorry. Sorry. So this circle is again tangent to the three sides, right? Except it doesn't have to be in the segment. Now we just no tangent to the whole line. So here, this is called the AX circle, and its center is the AX center. So again, we have the angle bisector properties, right? If you just ignore BC, it's literally just two lines and a circle that's tangent to both of them. So by symmetry, they must lie on the angle bisector. How do we define it exactly? That's a good question actually, because I kept saying let there be an in circle without kind of explaining why there must be an in circle, right? Um, so so yeah, to exactly show that an in circle or an X circle exists, what we can do is to start by constructing the angle bisectors first by taking, let's say, two angle bisectors. So let's say, for example, for the in center, we take two of them first. Take two of them first, meet at that point. And then now I drop a perpendicular, I drop an altitude towards this side, and I draw a circle through it. Then you can show that it's parallel to, sorry, it's tangent to this again, because these two are equal since by symmetry. And it's equal to this again. So we can exactly show that the circle exists. Yeah, good question. And for the X circle, what we can do is to start with the angle bisectors, except now it's the angle bisector of what we call the external angle bisector of B. So if you have this, this is the internal angle bisector. The ones that's perpendicular to it is the external angle bisector. Why? Because it kind of bisects the external angle. It bisects these two. So we can take two external angle bisectors, and then we can draw a circle with that as the center and with this as radius. So next circle exists. Okay, so from the in-center and next-center diagram, I want you guys to look at more properties of it. For example, A, let's say this is A prime again, it's B prime, it's C prime. The convention is to just label it in relation to the vertex that's opposite it, so you don't get like messy labeling. Then AB prime is equal to AC prime. Again, by symmetry, assume B and C weren't there. It's just literally two lines and a circle that's like tangent to it. Or you can just you say, okay, it's just tangent to the in circle, so they two have they both have the same length. And these two have the same length, these two have the same length. Right? So if you solve the equations, you can show that, let's say the one A, this would be B plus C minus A over 2. B plus C minus A over 2. You can also write it as S minus A, where S is the semi-perimeter of the triangle. So you take the perimeter divided by 2. And you can kind of see this the same thing because you subtract A, you get this. Right. Let me get this here. S minus A, S minus A, S minus B, S minus B, S minus C, S minus C. Okay. Now, for this diagram, we can again, well, solve some variables. We can show that this two will be the same, and it will actually be S minus C. This one turns out to be S minus B. Okay. And this whole thing will be the semi-perimeter. Why is that? Okay. It's actually, you don't really have to solve equations. I mean, if you want to, it's just a very simple equation. You just put in X, Y, Z, solve for X, Y, Z. You can see, okay, first of all, these two have the same total length, right? Because they're both tangent to the big circle over here. They both have the same length. Now, and then the two, let me put this as green. These two are the same length. And then the two orange lengths are the same. Because again, by tangentiality, the two orange lines have same length. And the green line has the same length. So the green line is actually the same thing as this total length, right? This L, or whatever shape this is, this folded line. Where and on the other hand, the other green line is also equal to this plus this. I just kind of fold this length upwards here. So these two have the same total length. They add up to the perimeter of the triangle. So each of them must be equal to the semi-perimeter of the triangle. A plus B plus C over 2. Right. Makes sense? So, and then you can subtract c. So because it's c, so this is s minus c. So a non-trivial corollary of this is that if you draw the circle and the x circle, these two have the same length. These are two s minus b, s minus b, which is not very obvious, but by solving the side lengths, we can show that they are actually the same thing. Right? Is that okay so far? Yeah, but there are a lot of other points. Like you can have the nine point circle center, 9 point center. The what else? There's a nagel point as well. There's the what it's called. It's labeled by F. Uh, you know, it's not Frobenius. It's okay. There's one point that's also labeled by F. I forgot why it's called. If anyone knows, you can actually comment. Uh, yeah. So now let's talk about something else, which is some length chasing. So I'm not sure if right, so is everyone here familiar with the law of sines, the sine rule, or is everyone here not familiar with the sine rule? Okay, okay, okay. So there are people who don't know. So I'm gonna teach it first. So the sine rule or the law of sines. Yeah. So you guys probably learned it in high school, but as far as I know, they normally don't prove it to you why it's true in high school. So let's try to prove it here. So, yeah. So the sine rule, as someone said, it's a very neat rule. It tells you that the side lengths and the sines of the angles they form equal ratios, and this ratio turned out to be 2 times the circumradius, but that comes afterwards. It basically says, okay, another way of phrasing this part is that A, B, C, that ratio is the same ratio as sine A, sine B, sine C. I like to say it this way. I like to see it this way. It's kind of it's more tangible. It's better to imagine because it's quite symmetric in this way. Okay, so to prove this, and we can use we can use this clue, which is all three of them they are equal to this common quantity. So if you can prove that one of them is equal to this common quantity, then the other two would follow, right? So let's take a look at the triangle ABC. So the side length BC is lowercase a, and this is angle A. However, we don't really have a right angle for us to use sine, right? We want to have we want to have sines. So what I'm gonna do is put draw the circle. This perfect. There we go. Draw the circle. Then It's O. Now OBC is quite a symmetric figure. It's an isosceles triangle, and the angle above here is 2A. Right? These two are the same. These are in fact both equal to R. But this is A over 2. This is A over 2. And in fact, this is 2A. Remember this property? X theta, 2 theta. In this case, it's 2A. We split it in half. That means A and A. So sine A is A over 2 over R. So A over sine A is 2R. Right. Cool. So, well, this kind of proves the whole thing, because then you can do the same thing for B, you can do the same thing for C, and R doesn't change. R is still the same where whenever you relabel the vertices. Okay. Sometimes you might forget which side is which, like whether it's A over sine A, whether it's sine A over A, but it doesn't really matter since the ratios are the same. But if you want it to be equal to 2R, then well, one way you can see it is that sine A is normally the small number, right? Sine A is normally between 0 and 1. So 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 that cannot be on the numerator, otherwise you get a very, very small number. Or you can think of it in terms of units, like A and R, they're both lengths. Sine A is just a constant. So you can't have a constant over length be a length. Okay. So using the sine rule, it it tells us quite a lot of things. Like if we have an incomplete picture of a triangle, we can use the sine rule to kind of find out what's remaining, right? Like what's the remaining angle, what's the remaining length, and so on. So for example, you can use it to prove the angle bisector theorem. Bisector theorem. So you have a triangle, we have an angle bisector. So the in center is on the angle bisector, but that's not really important in this case. So if this is D, yeah, AB AC is the same as BD DC. I'm using regular lengths here. I don't care about the sign. So it's kind of like saying that this over this is the same as this over this. Yeah, so this is the angle bisector theorem. So how can we prove this? We can call this A over 2, A over 2. Yeah, so instead of looking at the so we can actually rephrase this, right, as AB to BD equal to AC to CD. We just bring the two things right to the other way around. And AB over BD is just this side length over this side length. And remember what we said about the sine rule. The ratios of the side lengths is exactly the same as the ratios of the sines of the angles. So AB over BD is literally the same as the sine of this over the sine of this. Right? Sine of angle ADB over the sine of angle sine of A over 2, basically. Yeah, and the same thing goes for the other side. This over this is the same as the sine of this. We can write that out. AC over CD is the sine of ADC over sine of A over 2. But these two are the same thing. So this is trigonometry, right? Trigonometry, the sine of an angle, same as the sine of its not sure what it's called, a supplement angle. 180 minus theta. The theta here is well, it's any angle. This is always true for all angles. So if you use a unit circle definition for trigonometry, then the sign is always the y coordinate of the point. So if you have theta and 180 minus theta, then they both have the same y coordinate. So they both have the same sign. It's the same, it's equal to the sign. So yeah, so these two are the same and the bottom are the same. So the two ratios are the same. Right. Okay. Uh, what do you mean AC over CD is equal to this divisible by? No, it's nothing to do with divisibility. Oh no, sorry. I was just making a divider. Yeah. Yeah, these two are the same. Okay. Well, this is actually the internal angle bisector theorem. You can have an external angle bisector theorem as well, which is quite cool. So if we have this is the internal angle bisector, you can have the external angle bisector. So that will be something like this. And if you so instead of meeting here, D1, you meet BC at D2. Then in this case, AB over AC is equal to, well, it's actually the same formula, in fact. In this case, B instead of BD1 over BD1C is BD2 over D2C. So it's a bit weird because you're kind of moving here and you're moving back instead of just now that we're just doing this, right? But the point is that these two ratios are the same thing. They are both equal to the ratio of this by this. Okay. Well, this is a very similar proof for this, in fact. Very similar proof. You can use a sine rule to prove it. So, and there are major implications of this because now this tells us that the green ratio is equal to the pink ratio. BD2 over D2C equals BD1 over D1C. And this, I'm not going to go into details, but if you're interested, this means that D2B, D1C, they form what we call a harmonic bundle. They form a harmonic set of 4 points. And you can do quite a lot of things with that, but it's a bit too advanced. So, okay, yeah. Anyway, speaking of lengths, we have the sine rule. We can we can derive a very nice theorem called Siva's theorem and Menelau's theorem. So they are kind of the same thing, in fact. It's just in a different configuration. Wait, let me think. Okay, not really the same thing, but still, they are very similar. Siva's theorem looks nicer. It goes like this. Let's say we have ABC and we have a point inside, any point. In fact, it could be outside as well, but I don't want to make it complicated. Now, if you draw the three lines, this is what we call a set of Sevians. So basically, like three lines from vertices that concur. Conquer anywhere. They don't have to conquer in the triangle, they can conquer outside of the triangle as well. But the point is, now that we have these intersection points, it says that AB prime over B prime C times CA prime over A prime B times BC prime over C prime A is equal to 1. And actually, this is using signed lengths. But you don't, well, you don't have to look at it in terms of signed lengths because normally they're all positive anyway. So it says if you cycle through from here to here, then from here to here, and down here, you look back to the same ratio. You look back to 1, which is quite a nice thing. That means if you know 2 of the other ratios, you can find the third ratio. Right? Well, in fact, this I will leave as an exercise to prove. You can basically convert this theorem into the sine rule, and then you can convert it into to sines of angles, and in the end, the sines would just cancel out. Okay, that makes sense. The sines would just cancel out. So maybe you can think of like angles inside here and angles on top of here. In the end, they will cancel out. Right? Okay. But I can give you a hint. You have to involve these 3 lengths as well. Actually, I can talk a little bit about it. The angle bisector theorem has a generalized version. Generalized version is this. So it's not really appropriate to call it the angle bisector theorem anymore because it's not really the angle bisector right now. It's any line. Say this is theta, this is phi. Then it says that BD over DC is AB over AC times an extra factor. So this extra factor is basically the ratios of the 2 angles up there. And you can prove it exactly the same way as you prove the angle bisector theorem. So sorry. Uh the sine of theta over the sine of phi. So normally I kind of forget which one is on top of which, but if you think about it, well, if theta is 0, then BD over DC is 0, so it couldn't be the other way around, so it must be sine theta on top. Yeah, you can call it the ratio lemma or whatever. I don't remember names anyway. Yeah, okay. So you can use this thing, and if you apply it to, let's say, this triangle, and then you apply it to the other triangle, and like to this one and to this one, you can derive, you can basically prove this quite quickly. Now, Siva also applies to points outside the triangle, which is quite ugly. So if D is, let's say, here instead, then yeah, D is here, then we can define, we want to call it D. Yeah, let's call it just D. So this point is now A prime. A prime. This point is now B prime. And this point, oops, no space over here. This point is now C prime. And the same ratio lemma holds. I mean, the same ratio relation holds. So Siva theorem also works when B is outside of the triangle. So in this case, it's going to be quite messy because you have AB prime, B prime C, and then CA prime, A prime B, and then BC prime, C prime A. So it's kind of in this weird direction. But there is some sort of pattern to it. You're basically, yeah, you can kind of see some pattern to it. You basically start at a vertex and you walk across to the nearest intersection. I mean, not nearest. You walk across to the next intersection point, and then you continue walking to the next vertex. And then you change direction and go to the next intersection point, and you go to the next vertex, and then you go to the next intersection point to the next vertex. You can kind of see some pattern to this path. And that's going to be important because we're going to use it in the Menelau's theorem. Yeah, you can think of it as like walking. I mean, it's a nice way to remember it. So like you see A, I go to B prime, and B prime I go to C, and C I go to A prime, A prime I go to B, C prime and then A. So you can kind of see like vertex, intersection point, vertex, intersection point, vertex, intersection point, vertex. Uh, I don't know. Well, I don't mean walking in any serious mathematical sense. I just mean like casually, if you're standing here, you just walk in that direction. Hmm. Yeah, but walk is a thing in graph theory, but it's nothing to do with what I'm saying here. So, Manuel's theorem is instead of Siva is where you have a triangle, say point, right? And then you have a bunch of ratio stuff that comes up. The Menelau's theorem is a triangle, and you're given a line, and then you can give birth to a lot of ratios. So now assume that you have a triangle, and you have a line L instead of a point. I'm going to define A prime, B prime, C prime very similarly. So A prime would be wherever this line L meets BC, and B prime would be wherever this line L meets AC. You kind of see a pattern here. You just basically look at the other two vertices. So let's label them right now. A prime. So line L intersect AB, that's going to be C prime. Whatever's on the opposite side, just call it that thing prime. It's B prime. And Mendel's theorem is actually exactly the same equation as Siva's theorem once we label the A prime, B prime, C primes in this way. So it's AB prime over B prime C times CA prime over A prime B times BC prime over C prime A. So again, you start at the vertex, you walk to the next intersection point, walk to the next vertex, walk to the next intersection point, walk to the next vertex, walk to the next intersection point, walk to the next vertex, and you form a loop. Right? And they will be equal to 1. Except if you're working with signed lengths, they are equal to -1, but you don't really have to talk about signed lengths if the diagram is clear. Because you can kind of see there's one switch of direction right here, right? It's from C to A prime to B. So once you switch, you kind of straight swap the sign. Uh, yeah. So this is Menelau's theorem. Again, it works as well if the line is outside the triangle. In which case, your A prime, B prime, C prime, you define it similarly. The same thing holds. Yeah, yeah. Not gonna prove it. It is you can prove it the same way as Siva. It's not that convert the length condition to an angle condition. So when you have like Mendel's theorem, you can kind of solve a lot of length chasing problems. Like for example, if you have, let's say, a square, oops, a square, and okay, let's say we have this 1 to 1, and then you have this, let's say this 1 to 2, 1 to 2, then you can actually find what this ratio is, x to y, x to y. How do we do that? In fact, even though Mendel's theorem is about a triangle and a line, I sometimes like to think of it as this complete quadrilateral. I mean, this is what I call a complete quadrilateral. Or you can call it like whatever, you can call it whatever you like. It's like a fish or something. So, or like a mountain, whatever you want to call it. Uh, yeah, this is actually a square. But the fun thing is, even if it's not a square, the answer of x over y will still be the same. So it doesn't have to be a square, in fact. Oh, I mean, sorry, I mean like this, the ratios is 1 1. So k is like m to m. Yeah, but okay. So I like to think of this configuration as a complete quadrilateral. So something like this. And then you're kind of concerned with the ratios here, the ratios here, and the ratios here. And then you can apply Mendel's theorem by finding the remaining ratio. So now we have now we have the ratio here, we have the ratio here, and then we have this nice figure, which is consistent with Mendel's theorem. And you want to find this. So we can directly apply the theorem. So we can say, okay, uh, you can start anywhere. So we can say, okay, let's say you start here, go this way. So it'll be 3 over 2 times. Then we go down to y over x. And we go back up. That's 1 over 1 equals 1. So y over x is 2 over 3. So you can get a lot of ratios for this. And you can also get the other one by doing the other way around. Mm. So with this theorem, you can actually, it's quite powerful sometimes. But another powerful thing is you can use this to prove collinearity as well. So the fun thing about Siva and Menelaus is that the converse is also true, right? The converse is also true. If this thing holds, that means the three lines are concurrent. If this thing holds, that means the 3 points are collinear. Make sense? So this if and only if AA prime, BP prime, BCC prime are concurrent. And then this if and only if A prime, B prime, C prime are collinear. So that's why you sometimes want to talk about the sign length because you can handle that case. Because if you use regular lengths, these two are the same equation. They're both equal to 1. But configuration wise, you can directly tell apart whether it's the Siva case or the Menelaus case. You just look at the diagram. But if you want to make it formal, then you can use sign lengths and say it's 1 is plus 1, 1 is minus 1. Yeah. So now with Siva and Menelaus, we can actually prove a lot of the centers. the previous centers of the triangle. Like for example, the centroid. Prove that the centroid exists. You just have to prove that 1/1 times 1/1 times 1/1 is 1. Because that's where the medians meet, right? 1, 1, 1, 1, 1, 1. The ones here are ratios, not lengths. Make sense? And for example, if you want to prove the orthocenter exists, you can find out what these side lengths are, and it's not that hard to find these side lengths. In fact, it's just write it as a cos b or something like that. Once you find all of that, you multiply them together, they all cancel out, you get 1. Right? And to prove that the in-center exists, the in-center, why does the in-center exist? Well, this is the angle bisector. So if you meet it, if you continue drawing the lines, then we can use the angle bisector theorem to find what this ratio is. And then to find what this ratio is, find out what this ratio is. Multiply them together, everything cancel out, you get 1. So the in-center exists. Now, how about the Gauguin point? The tangents. Well, this is also simple because, okay, we already found out that this is S minus B, S minus B, S minus A, S minus A, S minus C, S minus C. And now it's even more obvious how to use C bar. You just take this, everything cancels out. So it's 1. So the Gauguin point exists.
Tristan Shannon.
Hmm? Oh, well, someone asking a question. Never mind. Yeah, so the Gauguin point exists. You can prove it using this way. Right? Cool. There's an X circle variant of the Gauguin point, which is called the Nagel point. Basically, like the three X circle tangential points. We can get the Nagel point. But yeah, anyway, so now we have C1 Menelaus. Cool. Mm, then let's look at the next nice point called the 9-point center. A, B, C. Now, if we take the orthocenter, this, this, and like this, with H, right? Mm, these are the altitudes. Let's call them A prime, B prime, C prime. And I'm going to do something weird, which is you can take the midpoints of AH, midpoints of BH, midpoint of CH, and label them as well. Let's say A prime prime, B prime prime, C prime prime. Okay. Now we take hang on, we take the midpoint of BC, AC, and AB. I'm running out of primes now, so let's just call this A1, B1, C1. So X1, the X1s are the midpoints. Now we have three triples of points. We have 9 points. And the nice fact is that all 9 points, they lie on a circle. They are all cyclic. Really, really nice. But yeah. So this is a 9 point circle named after those 9 points. Okay. So, well, let's see why these 9 points are cyclic. And the x prime primes, the x prime primes are the midpoints of x. But like for example, a prime prime is the midpoint of AH. So x prime prime is the midpoint of XH, right? Where x is A, B, C. Okay, cool. So why? And it hinges on two lemmas, which are very, very, very nice problems on their own. So let's dissect this into smaller pieces. Once we have the auto center here, there's a very well-known lemma, and we're gonna try and prove it here if you all haven't seen it. It's that if you reflect the auto center over a side, it will lie on the circle. Oops, yeah, it will lie on a circle. If you reflect H over the midpoint of BC, it will also, well, lie on the circle. Reflect. It will lie on the circle. And this is a very direct angle chasing problem. You don't even need length chasing in this case. Um, Jia Heng probably already discussed this problem at some point with you guys when there's like angle chasing, when he was teaching angle chasing. You just prove that the angles add up to the 180. Like for example, why does this add up to 180? Reduce it to saying why does this add up to 180? Then you can kind of work your way out from there. So let's use these two lemmas onto this configuration and see what happens. So here's what's going to happen. This is our A prime. This is our A1. Okay. Our A prime is our A1. One here, one here. Now, what happens if I shrink the circumcircle from H? Right. So imagine I fix H and I shrink the entire plane from H with a scale of 1/2. Exactly, yes. With a scale of 1/2. So what does that transformation send? It will send this point, this point, this point, all these 3 points to the 3 points that we kind of see in the 9 point circle. Does every polygon have a circumcircle? Every triangle has a circumcircle. But once you get past three vertices, you cannot guarantee a circumcircle. Like for example, if you have a quadrilateral, right? Let's say you have a quadrilateral. So think of it, why can't we guarantee it? Because, well, triangles have a guaranteed unique circumcircle, right? So maybe these 3 points give a circumcircle, but maybe the other 3 points give another circumcircle. So then there cannot be a unique circumcircle. Unless in the rare case where they are the same, which means the 4 points are cyclic. Yeah, anyway. So once we shrink from h with a scale factor of a half, then we basically get the 9 point circle right now, right? So we're done. This also gives us a clue on where the center is. So we haven't talked about center. But, well, the center of omega is the circumcenter. So once you shrink it, it shrinks the same way. N9 is just the midpoint of OH. Oh, you draw it nicely, but hang on. OH is somewhere here. So N9 is here. 9 point circle. So yeah. Okay. All right. Mm, okay, with this. Time is oh, 8:39. Cool. So now we have three very nice relations. We have that H, N9, and O, they are collinear, right? They lie on this line, OH. Very nice. In fact, there are three other points, three other centers that also colline, and they form what we call the Euler line, and they are the orthocenter, the centroid, was somewhere here, right? G, and also the circumcenter. Oh, well, they are also collinear. So N9 is also on top. They all lie on the line OH. So this is called the Euler line. So the Euler line contains H, G, O, and N9, and a few other nice points, which I forgot their names, but they're not really important ones. Okay, so let's look at this case instead. Why is G on the line OH? So again, let's draw a circumcircle because that's probably going to be useful since there's a circumcenter over there. So ABC. So this is here. H and AG next to the midpoint, so M, and this is 90 degrees. Now, let's use a lemma we used just now. HM, H reflected across M, lies on the circumcenter, as the circumcircle, right? And then H reflected across this is also on the circumcircle. So in fact, since this is going to be 90, this is also 90, right? To a scale factor of 2, which means that this point, A prime, is the diameter of the circle because this is 90 degrees. So AO will pass through it. So now we have this. Let's remove some junk. So AO A prime, they are collinear. HMA prime, they are also collinear. So what does that tell us? Now let's look at this triangle over here. Let's look at these two lengths. They they are related by a homotopy from A prime, right? Imagine from A prime, I scale up OM, I'll get AH. But what's that scale factor? That scale factor is exactly HM over MA prime, which is 1, 1. So basically AH is twice of OM, right? AH is twice of OM by the homotopy. Okay. But remember what's also in the 2:1 ratio? The centroid with its median. This is also 2 to 1. AG is also 2 GM. By properties of the centroid. So prove that HG equals 2GO. Yeah. And why is that? Now that you have these two ratios. Now it's actually just a similar triangles problem. Because these two are parallel. These two are parallel. So whenever you connect OH, they also form the same ratio 2 to 1. Right? So they must be collinear. Okay, you can think of it this way. So let OH intersect AM be G prime. Because we don't know it's G yet. We want to prove that it's G. Right? We always have to get the logic of the proof correct. So we don't assume the result. Yes, we want to try to prove G is G prime. Because now when you have this G prime, we can talk about the ratios. Yeah, you can call it a technique called like phantom points, or whatever you want to call it. It's a very nice name. Uh, I mean, yeah, some people use the term phantom points, and we can use this technique to say why G is G prime, because now we know that AG is 2GM, right? So if you manage to prove that AG prime is equal to 2G prime M, then they will be the same because there's only one unique point that satisfies this relation. I mean, in this configuration, there's another point that satisfies it, which is outside of this line, but that's another point. So once we have, so let's focus on A H and then O M. These two are parallel. Let's connect these two at G prime. Well, that means AHG prime is similar to M of G prime, right? By simple angle chasing, which means okay, AHG prime, or let's say AG prime over G prime M is AH over M, so it's 2. Yeah, and hence G equals G prime because G also satisfies that, and there's only one unique point that splits the segment into 2 to 1. So of course, this proves that they're collinear, but the other ratio also gives us an extra bonus information, which is Hg is equal to 2GO as well. So bonus Hg over GO is now AH over OM as well, which is 2. So Hg over GO forms a 2 to 1 ratio. Okay. So the Euler line, you have H, you have N, 9, you have O, and then you have G, which is sort of like 2/3 the way. So we can kind of prove that this is in a sort of 3:1:2 ratio. Let's check. Yeah, 3:1:2. Yeah, still anything to ask? Anything to say? Cool. So the technique here is so far we've only been doing angle chasing and length chasing, and also previously the power of a point. So the point about geometry is that for the most basic kind of Olympiad geometry problems, angle chasing and length chasing are normally enough. So if you know your cyclic quadrilaterals well, if you know your if sometimes you can use a bit of bashing if you want, but if you know how to construct, let's say, these kind of phantom points and find out similar triangles, you're basically good to go. So sometimes when you look at a geometry problem, the first thing you can ask is whether there are cyclic quadrilaterals. That's normally what I ask myself if it's a G1 or a G, if it's a P1 or a P4, find for cyclic quadrilaterals. Or maybe some bundles that you suspect is a cyclic quadrilateral. Also, that's also a very good starting point. Similar triangles also, similar triangles, and things like that. Only when you sort of meet an obstacle, then maybe you could want to consider other options like well, sometimes we would use a bit of bashing, but if you want to use bashing, we use some neat bashing. We don't want to bash the whole problem because that's going to be very ugly. Uh, cool. Let's see. There's 10 minutes left. Not much I can say right now. But yeah, let's look at another application, for example, let's say, so to speak. Yeah, and also maybe your homework at these. Okay, this is just a rough guideline. It doesn't always work, but they are nice questions that you can ask if you want to start somewhere. Okay. Mm, right. Let's say we have a triangle. We have a triangle. The in center, in circle, sorry. And we have the X circle. Okay. Now, I draw this line like this. I want to ask, what can you say about this point? So this is a prime. This is a prime prime. You want to use your spatial reasoning very well. So there are two circles here. And now let's reconnect this line because now it's like a random line connecting the vertex to the x circle. And this line kind of randomly intersects another circle, and we're trying to ask what that point is. So we can't really do much of angle chasing right here because there are too many disjoint shapes together. So think of another way to analyze this. What properties does that question mark point have? And you want to look at the relationship between the two circles over here. Prime is the top of the x circle, and by homotopy the question mark y. Yeah, exactly. Yeah. So A prime prime. So first of all, the two circles here, the in circle and the ax circle, they're related by this homotopy from A, right? Centered at A. So whatever line that you draw from A, you would basically connect the two points under that homotopy. So now that A prime prime is like the topmost point, you kind of say, the topmost point of that circle. That means the question mark point is also the topmost point of that in circle, which means that this too is the diameter. Oops. Which means that like draw. Right, right. This is the diameter. It's perpendicular to this. Right. Okay. Yeah. So think in many ways. So we don't stare at a diagram and then trying to find angles. We try to look at it in many dimensions, many angles. Okay, cool. Now, in the last 5 minutes, I'm going to talk about isogonal and isotomal conjugate. Isogonal conjugates and isotomic conjugates. So an isogonal conjugate for a point is the point that you obtain by reflecting each Cevian across its angle bisector. So the question, of course, is why does P prime exist? Maybe you reflect them and suddenly it doesn't collide anymore. Sorry, it doesn't concur anymore. Right? That might be possible. But in fact it's not. So we can prove that P prime actually exists. So actually to do this, there's a very quick way, which is what we call the trigonometric version of the Siva and Menelaus theorem. So remember Siva and Menelaus just now? There's an equivalent trigonometric version, and it's actually just a sine rule again. Basically convert the lengths into angles. So maybe it's 1, 2, 3, 4, 5, 6. Siva actually can be said as sine angle 1 over sine angle 2 times sine angle 3 over sine angle 4. times sine angle 5 over sine angle 6 is equal to 1. This is the trigonometric form of the Siva's theorem. And Menelaus has its own as well. And it's the same way, you just change the lengths into angles. So whenever this holds, the three Sevians are concurrent. So that means we can immediately apply it here. If P is concurrent, this Siva relation holds. Now if we reflect the angles, the angles just flip. So Siva's theorem still holds, and so P prime exists. Right? Hopefully that makes sense. So P exists by Siva, it exists. So now I just swap the angles. Siva still holds because it's the same equation. Then hence P prime exists. Whereas the isotomic conjugate is, instead of by reflecting the lines over the angle bisector, you reflect the line by reflecting it across the midpoint of the Sevian, as in it is x, right? Then we look at x from this other direction, and we connect that instead. And then maybe we reflect this here, reflect here, and we reflect. It's very, very hard to draw. Okay, this looks like they all conquer at the point, but it's only the green lines conquer at this point. This is P prime. This is the isotomic conjugate, where you take the base of the Sevians and you reflect it across the midpoint. And why does this exist? Now we use the regular form of Siva, right? We use the regular form of Siva. If P exists, we have the length Siva relation. Now you're flipping the lengths, so Siva's relation still holds, and then you can get back and say P prime exists. So this is a isotonic conjugates. Okay, let's just stop here. I'm gonna give an exercise here, which is if you have two isogonal lines like this is D. You can actually prove that BD over DC times BE over EC is AB over AC squared. It's a very, very nice relation as well. Because now you can relate the ratio of one point to the ratio of its isogonal conjugate. I mean, it's not really isogonal conjugate here. It's just the isogonal because now we just take these two lines. Yeah. Okay. Yeah. Let's just stop here. Before we get to overtime. So any questions before we ratio lemma? Might work. Yeah, actually it might work. I think ratio lemma can maybe help. Let me see. Yeah, but in the end you can use sine rule to complete it. And this relation here is going to be useful when we talk about like isogonal conjugates when in barycentric coordinates, for example, but I'm not sure if we're going to say that. So, okay, cool. So we're going to end here. For the next session, which I will continue teaching, in fact, I'll open up to any topic that anyone wants to propose to learn as well. So, but like, I'm going to ask this afterwards. And I can just try and teach whatever you guys want to do. Okay, cool. So I'll see you guys in, when's the next session again? Is it in 1 hour? at 11 to 1. Okay, I think it is from 11 to 1. All right, I'll see you guys then. Goodbye.